I'm Reginald Hurchins, and my video presentation today will be on section 14.3, which is partial derivatives. Now, I want to start with the definition of just a derivative, which is the slope of a function at any one given point. Now, when that function has more than one variable, that's when you have to apply partial derivatives. And now this is the symbol for partial derivatives, dabbled. Now when you're doing it, the formal definition of partial derivative with respect to x is f of x plus h at y minus f of xy over h. Now the same thing except with respect to y, formal derivative is x, y plus h minus f of x over h. Now these both are first order partial derivatives. These are second order partial derivatives down here, this row. And this is with respect to x. You take the derivative of f of x with respect to x once, then you do it again with respect to x again, the second time. This is the same thing goes for y. Take it once with respect to y, then take it again with respect to y again. So that's twice. Now, you can do second order with respect to y first. So you take the derivative with respect to y, and then you take that same derivative and take it the second derivative with respect to x. And you can flip that and do x first and then y. And if you do those correctly, you should get, they should equal each other, the answers at the end. Now you can do third order and fourth order, but we don't really need to dive down and delve into those. We'll probably only go as far as second order. Now third order, you take y first twice, the first derivative then the second, then the third derivative would be with respect to x. Fourth order, y twice, once, second time, then x the third and fourth time. Or you could flip that and do x first, second, and then y the third or fourth.
Yeah.
So those were examples of how partial derivatives look or how they work. Now these are the theorems that
2, 1, go.
So this first theorem is the mixed derivative theorem, and it states that if the derivative of f with respect to x with respect to y and the second order xy are defined, then f of xy and f of yx are equal to each other. And I already showed that in the last examples. The second one says that if f of x and f of y are functions, then f of xy are continuous on an open region, and f of x is differentiable. The third one states that if f of xy is differentiable at x naught, y naught, then f of x is continuous at x naught, y naught. Now these last two both have to do with continuity, and we know that if a function isn't continuous, then it's not differentiable.
3, go.
Okay, so this is the example problem. F of x equals cosine x times y squared. And first you do the first order partial derivative with respect to x. And you hold y as a constant, so you take the derivative of the outside, which is cosine, derivative of that is negative sine. The derivative of the inside with y being constant is just take the derivative of x, which is 1. So you get y squared. You do the same over here, first order with respect to y. And you take the derivative of the outside, which is cosine, negative sine derivative. You take the derivative inside with x being held as a constant. So you get 2xy. Next you take the second order derivative with respect to x. Take the derivative of this. You get negative cosine. Take the derivative of the inside again. You get y squared, which equals the 4, y to the 4th. Take the derivative, second order derivative with respect to y again, and you get this right here. And then finally, take the second order derivative with respect to x and y, and then with respect to y and x. And if you do the steps correctly, you should get the same answer both times because they equal each other, as according to the last theorem we talked about.